Today's topic is called center of mass. There's a joke that says that physicists would approximate anything to a point in space, like even a cow. What it means is that physics is so complex that everything we've seen until now is assuming that everything is just a dot and that everything acts as a single point in space. So when we say a car moves, we're not actually considering it to be the whole car, but a point that represents the car. So physics works if you approximate a whole three-dimensional object to a single point that is exactly at the center of mass. So the center of mass is defined in terms of that. The center of mass, as I'm going to write here, is the point in which you can approximate a three-dimensional object and the physics still holds. So let's do an example of what this means. Suppose instead of having a single ball, you have two balls tied to a string, and they're exactly the same size. So you have a ball here and a ball here, and you tie them together. So the object is moving on the ground, and you want to know the speed of the object. But this one has a mass of 2 kilograms, and this one has a mass of 2 kilograms. So how do you say what the total mass of the object is and where the object is located? You put the object in the middle. You say it's the same thing as having an object here in the middle with a mass of 4 kilograms. And if you find the speed of a point in the middle of 4 kilograms, it's going to give you the same speed as the actual object that is two separate balls of 2 kilograms each connected by a string. So that's basically center of mass. It's looking for the place that you can locate and say, if the whole mass was concentrated in that place, everything, the physics, the speed, the acceleration, the mass, the height, everything would stay the same and still work. So there's an actual equation for how to do this. So if you have two objects, one we're going to call A and the other one we're going to call B, you need to find the location. This is XA and this is XB. The 0 is back here. And they have their own masses. Maybe now instead of being 2 kilograms and 2 kilograms, they might have different masses. So this one has mass A and this one has mass B. We don't know what it is. And we want to find the location of the center of mass. We want to find this point that can be in the middle, but if the masses are not the same, it won't be in the middle. So the equation for this is the following. The x, the position of the center of mass, so we call it Cm, is equal to the mass of A times the x of A plus the mass of B times the x of B all over the sum of MA plus MB, the total mass. Right? So if you do this and both masses are the same, you're going to get that it's exactly in the middle. But what happens if you have a bigger ball and a smaller ball? So if you had, for example, something like a really small ball and a really big ball, and you want to know how this moves, right? It's probably not going to move the same as if the ball was right in the middle. The center of mass of the object is closer to the big ball, right? And if you do the math with the actual masses, you are going to get the exact location closer to the big ball. But you can have more than two objects. What if on the other side you have another small object? If these two are the same and this one is in the middle, you might imagine that the center of mass is in the middle and you would be correct. If this one was a lot bigger, the center of mass of the three objects is probably maybe even inside of the third one. I would say it's something around here. Right? Because you're taking the three masses, but this one is clearly a lot bigger. So you can use the same equation with as many masses as you have. So if you have more than two objects, let's call them object 1, 2, 3, you would get m1x1 plus m2x2 plus m3x3 plus, and you can add as many masses as you have, and in the bottom you divide by the total mass, which is m1 plus m2 plus m3 plus m4, m5, and 6, as many masses as you have. So this is the actual equation for any number of masses for the center of mass in X. Now we can take this even further. What if the objects are at different heights, not only at different distances in X, but also in Y? So you could have a ball over here, you could have a big ball here, then you can have a small ball here, and a huge ball here. Right? So what is the center of mass of these four objects? Well, you would have to, just looking at it, I would say it has to be closer to the big one. These two don't do much. This one does a little. I would put it about here, around here. We would have to do the actual math with the masses to find out the distance in X, if it's here, 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 here. But we also need the height of the point, right? If these were not here, it would be higher up. But because these are here, it takes the point a little bit downwards, the center of mass a little bit downwards. So we need to put our axes wherever they go, and we need to find the x of each. So each one has a center at x and y. Each one has its own x and y, right? So we use both of these. So to calculate x, we use the same equation. So this point ends up having an x and a y of itself, the x of the center of mass and the y of the center of mass. The x, we know the equation, and the y one is exactly the same, but with the y's of each one. So you would do m1, y1 plus m2, y2 plus m3, y3 plus whatever else you have. And on the bottom, you still add the masses, m1 plus m2 plus m3 plus as many masses as you have. So using these two equations, you will get the two coordinates of the center of mass. So the center of mass is located in the coordinate point x center of mass, comma y center of mass. And you use each of these equations to calculate the x and the y. Now I'm going to erase and show you what happens if you have an actual 3D object instead of just separated points of different masses. So let's start with a two-dimensional object. Suppose you have a rectangle. So if you remember from chemistry, everything is made out of atoms, and atoms are like little balls. So what you have inside the rectangle, if you look at it with a microscope, is millions and billions of little balls inside of it. So you're going to have little balls. And if the density of the material is constant, like in any piece that you get, there's going to be the same number of atoms because the density is the same. So you could basically use this equation 1 billion times for every single atom that is inside of it and calculate the center of mass in X and the center of mass in Y. Of course, that would take you all eternity because there are way too many atoms inside of something. So there's a shortcut for this. Fortunately, if the density is constant, the center of mass is equal to the geometrical center of the object. So what we have in this case is that the center of mass is equal to the geometric center. So what does that mean? If you have a rectangle, where is the center of a rectangle? Well, you know, it's in the middle in height and in the middle in width, so it's probably around here. I don't know if I drew that correctly, but in the geometrical center. If you have an object that is like a triangle, you're going to get it in the geometrical center of the triangle. Yeah, if you have a circle, it's going to be in the geometrical center. If you have a sphere, imagine this is a sphere, it's also going to be in the center. If this is a bar, it's going to be in the center in the 3 dimensions. So that's what we can do when we have constant density. If we don't have constant density, like for example, a human being, where is the center of gravity of a human being? The basic idea is that depending on where the places are more dense, the center of mass is closer to the densest places and farther away from the less dense places. But for now, we're going to look at things with constant density where you know that the center of mass is the same as the geometrical center. And finally, you might be wondering why we went on to talk about center of mass if we were just talking about momentum last class. what is the relationship between these two topics. And the truth is, center of mass is always taught as part of the unit on momentum, because the law of conservation of momentum that we learned last class is actually talking about the center of mass. So the law of conservation of momentum says that the momentum of the center of mass is conserved if there are no external forces acting on it. So let me write that down. So law of conservation of momentum, the momentum of the center of mass is conserved if there are no external forces acting on it. So I'm gonna, to end this video, I'm gonna show you 3 examples of conservation of this law of conservation of momentum that have applications in real life. So the first one that I want to talk about is, suppose you have an explosive. You're holding a bomb that is going to explode, and you throw it in projectile motion. So if nothing happens, the bomb doesn't explode. What would happen is that you throw it, it goes up, reaches its peak, and goes down, and falls here. But what happens if in the middle the ball explodes? So it didn't reach this endpoint. When it was in the middle, it exploded into, to make it easier, let's say 2 pieces. So there's an explosion, right? And it breaks in half. And one piece falls right down. And it ends up here. Half of the bomb ends up here, like in the middle of the trajectory, right? And we want to know what happened to the other half. Well, the explosion was an internal force. It was not an external force. This means that the momentum and all of the laws will stay as if there had been no explosion. So the center of mass of the object still has to fall where it would have fallen if it hadn't exploded. So if half of the ball is here in this middle, the other half has to be exactly at the same distance on the other side. Exactly at the same distance. So this distance from this half to here is exactly the same as this half to the point of the center of mass. And this actually happens. Like if you throw something and it explodes, the pieces will be distributed such that the center of mass of all of the little pieces is still where the explosion would have fallen had it hadn't exploded. So that's a really interesting thing, I think. A second example is, suppose that you're an astronaut, you're in space, you're doing your spacewalk away from your spaceship, and suddenly the cable disconnects, and you end up flying off in space like in the movies. You're just there, you're maybe 1 meter from your spaceship, but there's no way to get there. You can't swim in space because there's nothing to push back that would push you forward. So what can you do? So there's the spaceship here. I don't know how to draw a spaceship, but suppose it's something like this. And you're here, you're a little astronaut, you're flying in space, you're screaming, help, because you're out in space and there's nothing to do. But fortunately, you have a backpack and you paid attention in physics class. So your center of mass is right there, where you are. And there are no external forces, there's no one to come pick you up. But what you can do is that you can throw your backpack. You can throw your backpack in the other direction. So now after you throw your backpack is over here. So if your backpack is there, but your center of mass has to stay here, what's going to happen with you? Well, you're going to be propelled in the opposite direction. So the little guy is going to go here, back to the station. That happens because the mass of the backpack went to the right, so your mass has to go to the left to keep the center of mass there. And that actually happens. That would actually help you go back. And the third example that might happen more often is you're in a little boat and you end up far away from the shore. Suppose this is the shore. You're on your boat. And you're scared because you dropped your paddles and you have no way of going back to shore. And the boat is so big that you can't reach the water, whatever, you just can't get back. So you try to walk forward in the boat, You try to walk to the right, but the center of mass will stay here. So if you walk to the right, the boat goes to the left. And you end up being exactly in the same place that you were before. So you walk to the right, the boat walks to the left, and you're not going to get any closer by walking on the boat. You might have tried that on a boat. You walk and you're pushing the boat behind you, so you basically stay in the same relative position as where you were before, relative to the shore. So what you could do is throw something. You know, you have a backpack, you say, I don't care about the backpack, I just want to survive. So you throw all of the stuff that you have to the left, you throw everything. And because the center of mass has to stay there, if you throw enough mass to the left, you and the boat will go to the right. And you'll end up here, very happy. Woo. As you can see in these three images of balancing, center of mass is what is used in order to balance objects. If you know where the center of mass of the object is, and you place your finger or a support right below that point, then the object will not fall, because gravity basically acts on objects at their center of mass.